Hi everybody. Hope you're all having a good day today so far. Today we are going to talk about linear functions. So we're still going to be in vector spaces. That's where linear functions make any sense, where they're defined. And so let's start off by saying that we have a matrix. So let's start off with an m by n matrix. So let's say, suppose A is an m by n matrix. Then there are a couple of things that we can say about multiplying a matrix times a vector. And one of them is that for any two vectors in Rn, it's going to be the case that A times x plus y times the sum of these two vectors is equal to ax plus ay. And the second thing we can say is that for any vector and any scalar, that A times that scalar multiple of x is that same scalar multiple of A times x. So those are just two. Once we know about multiplying a matrix times a vector, then these are just two obvious results that we get for doing that. But you'll notice that what I have is the arguments in here, not really the arguments, the vector that's being pre-multiplied by the matrix. This is the vector that's formed by vector addition of these two vectors, and this is the vector that's formed by scalar multiplication. And that's kind of the key as to why I wrote these two consequences here. So let's say if we now define a function from Rn into Rm in terms of the matrix being multiplied by a vector in Rn. So we'll say that for every x in Rn, f of x is A times x, then we can rewrite these two statements here in terms of f instead of in terms of A. And I'm now going to name those two statements L1 and L2. And so here we have, for every x and y in Rn, we have f of x plus y is equal to f of x plus f of y. And of course, that is just simply rewriting the first equation up here because f of x plus y is A times x plus y, and f of x plus f of y is ax plus ay, given that this is how we've defined our function f. And similarly, of course, I can rewrite the second statement for every x in Rn and every scalar. It's the case that f of lambda x is equal to lambda times f of x. Again, just rewriting the two statements up here. Now, it turns out that there are lots of situations in vector spaces where we have functions defined on a vector space and mapping into perhaps just the reals or to another vector space. It happens there's a lot of situations like that where the functions that we encounter have these properties. So I think you are probably not going to be surprised to hear me say that because these properties show up in all of these contexts that we will elevate this result, you could think of it as a simple result here, to a definition. And so that's what we have over here. So now I have a definition in which Rn and Rm, the domain and the target space of a typical function, have been replaced by vector spaces, arbitrary vector space V and an arbitrary vector space W. And now we say that a function that does this is to be called a linear function. So we say a function from vector space V to a vector space W is a linear function if it does exactly what L1 and L2 say here, and I even named them L1 and L2 over here. And of course, L, just like we used V for the properties that define a vector space, we're using L for the properties that define a linear function. Now, this could be confused with linear functions, linear real functions. And so I'm going to come back to that possible confusion or ambiguity a little bit later in the lecture. But let me just mention now that linear functions, there's other names for linear functions. So people also call them, I'll just use L for linear transformations, linear map from a vector space V into a vector space W. And because of this confusion that could arise, that I'll come back to that a little bit later, I'm going to use, and I'll try to use this as much as I can during the course, I'm going to use the term pure linear function for what we've defined here. So now we actually have four, if you like, synonyms: linear function, linear transformation, linear map, and this idiosyncratic, I use this, pure linear function. This is not something that's common. These are all quite standard, but I think this is actually useful. So a linear function, or a pure linear function, is just simply a function that satisfies L1 and L2. So the first thing I want to do now is actually derive a result about linear functions, not just about functions on Rn into Rm, but I've maintained that this happens in lots of situations that aren't just Rn and Rm. And so we're going to see a result, it's just a remark because it's really simple, a result that applies to all linear functions, any vector spaces. So let's put that remark here. So we'll say that a function from, well, let's make these vector spaces now. Let's not use it. It'll be true for Rn and Rm, but this is a more general result. So I need to write in here f from V to W is a linear function. So it's obviously a function because I've written f from the domain V to the target space W. It's a function, but it's a linear function. It satisfies V1 and V2 if and only if for all, let's write it this way now. I'm going to write V1, V2 in V, and for all, let's say alpha 1 and alpha 2 in R. And so what I've done here is I'm naming the vectors V's instead of X and Y because I want to use more than just two. So I go to X, Y, Z, W, and here I can just use the superscripts. And I'm using superscripts because I want to make sure I distinguish that these are vectors, and if I put subscripts, they might look like the components of a vector. So v super 1, it's a vector in v. V super 2, vector in v. And I'm using alpha 1 and alpha 2 because I want to have scalars with, in this case, subscripts, because there's no issue of them being vectors or components. And again, I may want to use more than 2, so I don't want to, I could have used lambda 1 and lambda 2, but I'm going to use alpha 1 and alpha 2 for a reason that'll actually become a little clear. So the condition here is that for any vectors and any scalars, f of alpha 1 v1 plus alpha 2 v2 is alpha 1 f of v1 plus alpha 2 f of v2. And so first, a couple things to notice. One, this is if and only if. So I have to prove it both directions. Another thing to do is to say, let's make this whole thing here, let's give this a name so we can refer to it. Let's call this, supposed to be parentheses there. Let's call this star or asterisk. And so we want to prove this. Again, it's if and only if, so we have to prove it both ways. Let's start by proving that if we have a linear function, then it satisfies this star condition. So that means we're proving that L1 and L2, the two conditions that define a linear function, imply the star condition. And so the star condition says that we've got any two vectors, any two scalars. So I'll just imagine that we've got arbitrary vectors and scalars here. And we've got f now of alpha 1 v1 plus alpha 2 v2. And of course, I can't just write on the right-hand side this because this is what I'm trying to prove. But what I can say is that L1 implies that f of the sum of this vector plus this vector is the sum of the images. So that means this is going to be f of alpha 1 v1 plus f of alpha 2 v2. That's just alpha 1 v1 and alpha 2 v2 are playing the role of the x and y vectors in the definition. And then, of course, L2 in our definition says that f of alpha 1 v1 is alpha 1 f of v1, and this is alpha 2 f of v2, and that's exactly what we wanted to show. So it wasn't anything deep or anything hard about this. Completely straightforward application of the properties L1 and L2 to this equation. So we've established that a linear function will satisfy star condition. And now let's go the other direction. Let's show that the star property will imply L1 and L2. And so let's first show that it guarantees L1. And of course, for L1, what I'm needing to show is that f of the sum of two vectors, f of v1 plus v2, is equal to f of v1 plus f of v2. So here we can simply let alpha 1 equal alpha 2, so we have f of v1, this should be equal to 1. Alpha 1 equals alpha 2 equals 1. And so we have f of v1 plus v2 is equal, that should be equal, equals f of v1 plus f of v2. So we've established L1, that the f of the sum of v1 and v2 is the sum of the images. And second, let's do L2, and for that, it's clear that we could say, for example, let alpha 2 equals 0. So that means that this equation here becomes f of alpha 1 v1 equals, that's 0, equals alpha 1 f of v1. So we have f of alpha 1 v1 is alpha 1 f of v1. So we've established L2, that if we have a scalar times a vector and we take f of that and get the image, then the image is going to be alpha 1 times the image of just f1. And in fact, let's even note that a way we can describe in words L1 and L2, and then I'll come down here with star as well. L1, we could say that L1 says that it's always the case that the image under f of the sum of two vectors is the sum of the images of those two vectors. And L2 says that the image of a scalar multiple of a vector is that same scalar multiple of the image of the vector under f. And star here says that the image of a linear combination. So note that this is simply an arbitrary linear combination of the vectors v1 and v2. And so star here says that the image of a linear combination, or at least a linear combination of two vectors, is that same linear combination of the images in Rm. Again, we should also note here that the vectors are in V, and I think I said Rm here. The images are in W. So we should point out here that the images, of course, are in W, and of course F, the image here, is in W as well, but the argument, these are vectors in Rn. So since this is just a linear combination of a pair of vectors, I could presumably say the same thing for an arbitrary linear combination with any number of vectors, and in fact that's the case. So let me write that down here, and I'm just going to replace this by saying that we could write star a little more generally. We could say f of alpha 1 v1 at alpha, let's say capital K, vk, and I'm using K, capital K here, because I could use n, but I don't want to get, or m, I don't want to get confused here. This is just a number, the number of vectors for which I'm taking a linear combination. I don't want that to be confused with the dimension of either V or W if they happen to be Euclidean spaces. So that's why I've used a capital K here as the number of vectors. And so this would be alpha 1 f of V1 plus out to alpha K f of VK. So we could actually write the star condition this way. Proof would be basically identical. We just carry it out for K vectors instead of two vectors. And again, note that it's if and only if. So since it says if and only if, this is it's a remark, so it's a characterization, but it's not a characterization theorem really. It's a characterization, an alternative definition, if you like, of a linear function. We could have defined a linear function to be a function that satisfies star, and then derived as a remark this definition up here that gives us L1 and L2. So that gives us a start on linear functions, and in particular, we have elevated these conditions or these properties to a definition, and we have now used just those two properties to establish this remark that we can write things in this different way here. So The next thing we'll do is to give a little bit deeper, not super deep, but a little bit deeper characterization theorem for linear functions on linear functions between finite dimensional vector spaces like these. So this characterization we're going to do will not work for all vector spaces, but it'll work for finite dimensional vector spaces, basically Euclidean space. So that's what we'll do next. We'll take some of this off, and that's what we'll do next when we get some space back. Okay.